Yes.
Thank you so much. So first of all, I'd like to thank the organizers for inviting me to this workshop. And I was asked to give a talk on Galprop, which is a code to model the synchrotron emission and the cosmic ray propagation in the galaxy. So first, I have to start by giving a generic overview of the physical processes behind, and then I will focus on the more technical aspect, and I'll give you some recent results. CMB and cosmic rays have been usually studied separately because they historically belong to two different communities. That means the radio microwave community for cosmic ray CMB studies, while the high energy community for cosmic ray studies. But this approach actually provides known limitations that we'll see in a moment. This also brings to the fact that there are two aspects of the galactic synchrotron emission, one bad and one good. The bad aspect is that it is a source of background, and it is something we want to get rid of for CMB studies. The good aspect is that it provides a lot of information on cosmic rays and also on the content of our galaxy. So let's see this in more detail. So here we have the 408 megahertz map that we all already know. We look at this map and we say, wow, this is synchrotron. This is usually used as template for the template component separation, and usually with assumptions of a spectral index -3 for the entire galaxy. But we know that the synchrotron intensity depends on the magnetic field intensity and the cosmic ray electron density, while synchrotron spectrum depends on the cosmic ray spectrum and on the magnetic field intensity. So we cannot safely assume that the synchrotron spectrum does not change much in different places of the galaxy. And also, to complicate the picture, the observed synchrotron emission is the integration along the line of sight of the entire emission. Our knowledge of the galactic large-scale magnetic field comes from various observables, and at present it is very limited. It is believed that there are three components of the magnetic field: the regular, the anisotropic random, and the isotropic random component. The regular component is traced by rotation measures, the parallel component only, actually, and also traced by synchrotron polarized and synchrotron temperature. The anisotropic component is traced by polarized synchrotron and also synchrotron temperature, while the isotropic random, also called turbulent component, is traced by the synchrotron temperature only. And actually, synchrotron traced the perpendicular part of the magnetic field along the line of sight. And as a consequence to this picture is that our present knowledge of the magnetic field is very limited. On the other side, also the knowledge of the cosmic rays is very limited as well. So let's see some challenges. First, direct measurements of cosmic rays such as Pamela or AMS to trace the cosmic rays at Earth. And they do not resemble the cosmic rays outside the heliosphere. In fact, there is the solar wind pushes away the cosmic rays and prevents cosmic rays from entering the solar system, especially the low energetic cosmic rays, as we see here in this cartoon. So this is called solar modulation effect. And second, we have also the cosmic rays in the interstellar medium may also not resemble the cosmic rays across the galaxy. Third, different energies of cosmic rays may have different distributions in the galaxy. And this is connected to cosmic ray sources and propagations and so on. And one additional important challenge is that cosmic ray electron spectrum and distribution are modified by the magnetic field itself. So the degeneracy and interplay between cosmic rays and magnetic fields has started to be accounted for only recently. And historically, on one side, the configuration and the intensity of the magnetic fields were not considered fundamental for galactic cosmic ray studies. On the other side, magnetic field studies have often assumed equipartition approximation between cosmic ray electron density and magnetic field density. And they also have assumed not physically based distribution and spectrum of cosmic ray electrons. So what do we model first, the magnetic field or the cosmic rays? I definitely think that they need to be modeled together at the same time by accounting for the interplay among them. Given the complexity of the physical processes, I'll try to simplify them as much as possible. Let's suppose that this is our galaxy. The galaxy is filled by cosmic rays. Cosmic rays are injected in the interstellar medium from sources, most likely supernova remnants, with a certain spectral index that we see here at the top here. And this is in proximity to their sources. Then cosmic rays diffuse for 10 to 7 and even for 10 to 9 years in the interstellar medium. And their initial spectrum and composition change. There are interactions of cosmic rays with interstellar medium that generate secondary nuclei and isotopes, antiprotons, secondary electrons, and positrons. And these change the composition and the distribution of all cosmic rays, including electrons and positrons, while they propagate in the galaxy. So during propagation, cosmic rays are affected by energy-dependent diffusion and energy losses that steepen the spectrum, especially the high energies, and they depend on the magnetic field. Also, acceleration processes change the spectrum as well. And finally, close to the Earth, the solar modulation effect, the solar modulation that we have seen before, that introduced before, affects also the cosmic ray spectrum, especially the low energetic cosmic rays. And in this energy range, the low energetic cosmic rays, it's the place where the propagation parameters are actually defined. The variety of the cosmic ray measurements for the various species provide information on propagation. In fact, for example, we have secondary to primary ratios, such as boron to carbon ratio that gives information on diffusion, convection, or acceleration processes. And we have radioactive secondary to primary, like, for example, beryllium-10 to beryllium-9, provide information on how far cosmic rays can propagate and so on. So this information directly reflects on cosmic ray electrons and positrons across the galaxy. To trace density and spectra of cosmic ray across the galaxy, we have to account for all of these effects, and we need propagation models. These models are based on cosmic ray direct measurements that reflect cosmic rays in this particular place of our galaxy, which may not resemble the spectrum and abundances of the entire galaxy, by the way. So to obtain information on cosmic rays in different places of our galaxy, I use also multi-wavelength observations of gamma rays and radio and microwave produced by interactions of cosmic rays with the interstellar medium to get much more constraints. And indeed, this emission provides information on cosmic rays in the entire galaxy far from Earth. These emission mechanisms are summarized here. So in gamma rays, we have pion decay by hadronic interactions of cosmic rays with gas, bremsstrahlung and inverse Compton in gamma again, with electronic interactions with interstellar gas and photons, respectively. And on the other side of the electromagnetic spectrum, we have synchrotron emissions in radio and microwaves, which is produced by the same electrons and positrons that produce inverse Compton and Brechstrahlung in gamma rays, and they by spiraling in the large-scale magnetic fields. So each component have a peculiar spatial and spectral distribution, as you see here, and they are very difficult to separate even in gamma rays. The Galprop code accounts for all of these processes. It is around since '98 with Strong and Moskalenko as the original developers. It models all cosmic ray species and gamma rays. And it was extended to include also synchrotron emission. And we included the possibility of calculating the temperature and the polarization synchrotron emission, so having a Stokes parameter, I, UQ, and also having 3D magnetic field configurations. And we implemented there to get the three components, a random, regular, and a possibly anisotropic random component. And we also included absorption so that we can also go to lower galactic altitude, for example, latitude, for example, and also at lower frequencies in radio. And the best model for the synchrotron spectral index that we found in this work, in our previous work, was used for generating the Planck separated component maps, which were officially released by the Planck consortium. I report here some examples of the synchrotron modeling for different cosmic ray electron distributions that you see here at the bottom. So various propagation halo size on the left, and with different cosmic ray source distribution on the right, compared with the 408 megahertz map. And this is to show the different synchrotron spatial models we obtained using a few regular models from the literature. So these are pretty old model, actually. It was of work back in 2013. So, and these are the predictions, while these are obviously the data, the polarized data of the alveolar map. And these are different models of the magnetic fields. These are examples of the synchrotron latitude profiles for a propagation model with a halo of 4 kiloparsecs on the left and 10 kiloparsecs on the right. So when feeding to the data, the halo size is degenerate with the offset map. So there are some parameters in the modeling that are degenerate with the offset of the map. And this is particularly important for some radio surveys where the offset is not known with a high precision. Some results from our previous works are here, reporting the following. So this was the first time the total polarized synchrotron emission was studied in context of cosmic ray propagation. And we found a high degeneracy among magnetic field and cosmic rays. And we estimated and included 3D magnetic field models and also estimated the intensity for various cosmic ray models. And we found the need of having an isotropic component of the magnetic field, and also the preference regarding the model of a flat cosmic ray source distribution in the other galaxy than usually assumed, and also a preference of a higher halo propagation size than 4 kiloparsec. And we also defined some offset in the radio maps, and we find that to be degenerate with the synchrotron model assumed. And also we could identify the best model, and that was used actually for the average of that model in the sky was used for separating the Planck foreground components. But let's see now Galprop in details. So Galprop solves the transport equation numerically for all cosmic ray species. The transport equation describes the cosmic ray flux, C, that you see here, that is the cosmic ray density per total momentum, P, as a function of position in the galaxy, R, and time for each cosmic ray species. In this equation, the first term on the right is like Q, describes the cosmic ray source term. That means the spatial distribution and energy dependence of the cosmic ray sources. During propagation, the particles are affected by spallation processes and nuclear decay that generate new particles. They are also called secondary cosmic rays to distinguish them from primary cosmic rays. So elemental abundances change, and tau F here is the time scale for loss by fragmentation. Tau R is the time scale for radioactive decay. As shown in this famous plot, the comparison of the elemental abundances of cosmic rays with respect to the solar system indicates which elements are secondaries, such as lithium, beryllium, and boron, for example. And in more detail, the secondary nuclei provide evidence of the propagation history of cosmic rays and also allow cosmic ray propagation to be probed, which is actually the interest of our effort. So in fact, secondary to primary ratios calibrate Galprop transport parameters for each model. And so we can get a clear picture of the cosmic rays, and not only of the cosmic rays, the propagation, but also the magnetic field, which are interested in. This term describes the spatial diffusion of particles in the galactic magnetic field. The diffusion identifies the walk around the random magnetic field lines, where dxx is the spatial diffusion coefficient, and in general it is found, it is a function of position, momentum, and magnetic field. This term describes the convection. V is the velocity, convection velocity, and it is a function of the position in the galaxy, and it depends also on the galactic wind. If diffusion occurs in the interstellar medium, the particles gain or lose momentum. Then there is diffusion in momentum. So this is due by scattering of magnetic turbulence, which is also known as a Fermi second order mechanism. It's like a ping pong. If the magnetic mirror is moving toward the particle will increase energy upon reflection. Instead, head-on collisions are more frequent than following, so particles in average can gain energy. So during propagation in the galaxy, cosmic rays are affected also by energy losses. The plots show the time scales of energy losses as a function of cosmic ray energy for nuclei on the left and for electrons and positrons on the right. These are calculated with Galprop in an average galactic hydrogen photons and magnetic field density, and also for given models. Ionization and Coulomb scattering are higher at low energies, while for electrons, inverse Compton and synchrotron are dominant at high energies. So we are interested in this conference on this part here. Even though somehow complicated, it seems that everything should be fine in the modeling, but actually it is not. So the issue is that the code is not just plug and play, unfortunately. And also it is not that Galprop can provide the cosmic ray electron distribution and spectrum to be used independently from the propagation itself to model the synchrotron emission, so they should be done together. So to give some examples, the magnetic field is responsible for energy losses that steepens the spectrum, and also magnetic field is also responsible for diffusion. So anytime we change something in the modeling or in the parameters, let's say, for example, we change the magnetic field formulation or the intensity, we also need to start again the process of checking all of the other observables and refit once more the various parameters to the different observables and try different possible scenarios also. So moreover, there are the ingredients of the Galprop code that are also the major source of uncertainty. The usual method is the following. We use cosmic ray direct measurements to constrain injected spectrum and propagation parameters. For a given cosmic ray source distribution, best constrained possibly with gamma rays. And given gas distribution to produce secondaries, also important for synchrotron. And we also need the magnetic fields and interstellar photon distribution model. All of these need to have 3D formulation. I use a multi-messenger approach that helps mitigating uncertainties in order to obtain a consistent model of cosmic rays, their propagation, and also the magnetic field and interstellar emission as much as possible. So once more, in other words, cosmic ray propagation in the galaxy produces interstellar emission that extends from radio, microwave, and gamma rays. Radio and microwaves are produced by synchrotron emission of electrons in the magnetic field, while gamma rays are produced by the same electrons and positrons, and of course also hadrons interacting with photons and gas in the interstellar medium. So I put together these observations plus measurements of cosmic rays, latest from Voyager, for example, and MSO2, and I use Galprop for modeling the propagation of the galaxy. I show you here the procedure that I use with the Galprop code for modeling synchrotron emission and get information on cosmic rays and magnetic field. So for a given cosmic ray electron spectrum, a given magnetic field, and a given distribution of cosmic ray sources, I obtain a propagation model parameters to input on Galprop. Then I compare the model, the polarized emission model with the data, for example, Planck. As a result, I obtain the regular magnetic field intensity by fixing then the regular magnetic field intensity and then compare and fix the microwave or radio temperature data, for example, the 408 megahertz map, and adjust the random magnetic field. And also galactic profiles are also investigated. But anytime the magnetic field is adjusted, we have to run again the Galprop and refit also the inputs such as the propagation parameters. And it would also be best also to check gamma ray data. This is one of the latest results. It is the synchrotron spectrum for intermediate regions that identifies the local spectrum calculated from this electron spectrum here at the top in the small box. So this is the electron spectrum, this is the synchrotron emission spectrum. So we obtained the red spectrum by comparing the gamma ray spectral data together with the latest cosmic ray measurements. And this is the red electron spectrum here, reproducing Planck and also the radio surveys spectral data. So by using, this is the best all electron spectrum that can reproduce actually this data. Other possible models that you see here substantially affect also the synchrotron spectrum in this way, steepening the spectrum or having much more intensity here than the surveys in the radio frequency band. This is an additional recent result. We checked the effects of the magnetic field on the inverse Compton spatial templates, inverse Compton in gamma rays. So these maps show the differences between two models of the inverse Compton. Different magnetic field models produce also different inverse Compton models. Such an effect also applies to any cosmic ray source distribution, gas, or interstellar radiation field model used. And this is why I say that we need to study everything in a multi-frequency approach. So to come back to our initial question, what do we model first, the magnetic field or the cosmic rays? Actually, the answer is that they need to be modeled together at the same time, in my view, by accounting for the degeneracy and the interplay between them, and also by using multi-messenger data and cosmic ray propagation models. And this is almost it from my side. So I thank you very much for your attention, and I'm happy to take your questions.